Now I want to give a geometric interpretation of integrating a function of two variables. So here we're looking at the graph of a function f, which is a function of two variables. And you can see the graph of f, the graph of our function f is a surface. It's the surface here. And we're integrating f, our function, over this rectangle that you see here. And the geometric interpretation of this integral is that we're computing the volume of this region under the surface, this three-dimensional region under the surface. We're computing the volume of that region. And let's look at what we're doing here. This rectangle, which is the region that we're integrating over, we have chopped up that rectangle into tiny pieces, tiny little pieces. And we're computing the contribution of each piece, and we're going to add up all those individual contributions. And now let's look geometrically, how do we compute the contribution of this piece? Well, what we're doing is we're computing the volume of this little three-dimensional column. And the volume, how do we get the volume of this rectangular column? Well, we multiply the area of the base times the height. And the height is f of what they're calling here xij star, yij star. So we're looking at this tiny little rectangle. We have selected a point xij star comma yij star inside that rectangle. And now we're visualizing this three-dimensional column. The height of the column is f of xij star, yij star. We multiply the height by the area of the base, and that gives us the volume of this three-dimensional column. That's the contribution of this little piece. And then we add up all those individual contributions, and what we get is a good approximation to the total volume of this region under the surface. So that's our geometric interpretation of integrating a function of two variables over a region in the plane. We're just computing the volume of the region under the surface.